Hello, my name is David Stim, and this is the physics of potato cannon. Let's begin with some background information on how potato cannons work. A potato cannon is made of three distinct components: the barrel, the combustion chamber, and the end cap. Let's look at each of these individually. The barrel is the part of the potato cannon where the potato sits. The edge is filed down to a point on all sides to ensure a snug fit is able to be created between the potato and the inside of the barrel. The combustion chamber is where the combustion reaction occurs. In this lab, a simple store-bought hairspray will be used as a fuel source. Inside this hairspray is a simple propellant which contains a simple hydrocarbon. When coming in contact with thermal energy, this hydrocarbon, in the presence of oxygen gas, will produce H2O and CO2 gas. The end cap is the driving force of the reaction. A simple flint and steel is threaded through the end of the end cap. When flicked, it generates a spark. This is used to initiate the combustion reaction with the propellant. The process of firing a potato is actually very straightforward. First, a potato is loaded through the barrel and fed all the way down to this coupler. The potato will sit right here. Then the combustion chamber is loaded with hairspray and sealed off with the end cap. When the flint and steel lighter is flicked, the combustion reaction occurs and CO2 gas is produced. The production of the CO2 gas inside the combustion chamber creates a pressure difference on this side and this side of the potato. This causes an imbalance in the forces being exerted on the potato and forces the potato to move up the length of the barrel and out the end of the barrel with incredible speed. This leads into a proposed question regarding the potato. What is the magnitude of the force exerted on the potato when fired from a potato cannon? To solve this problem will require the use of the impulse and momentum relationship. The force exerted on the potato occurs for a short period of time. CO2 gas is produced in the combustion of the hydrocarbon found in the hairspray. Once the potato exits the barrel, the only force acting upon the potato is gravity. Given that the mass of the potato and the initial velocity of the potato in the spud cannon can be easily determined, the time taken for the potato to exit the barrel and the exit velocity of the potato from the spud gun must be determined. But first, a few assumptions must be addressed. For the purposes of this lab, the air resistance on the potato will be considered negligible. The static and kinetic friction between the potato and the inner lining of the barrel will also be considered negligible. This will just simplify the mathematics involved in solving for the magnitude of the force applied. The procedure for this lab is relatively straightforward. The process of loading and firing the potato cannon was described previously. In this lab, a rig was developed to hold the potato cannon at an angle of about 30 degrees with the earth. The combustion chamber was then filled with hairspray from an aerosol can for exactly 3 seconds in each step. This ensured that enough hydrocarbon was present for adequate combustion. A timer was then started the second the flint and steel lighter was flicked. The timer was then stopped the second the potato hit the ground. A measuring wheel was then used to determine the distance from the potato traveled from the potato gun. A balance was also used to determine what the mass of the potato was. This is the data collected from 2 trials. The angle of the spud gun remained constant. The horizontal displacement was relatively the same, as was the time in the air and the mass of the potato in each trial. For the purposes of calculations, the data from trial 1 will be used to determine what the magnitude of the force is. The first calculation will help us determine the vertical displacement of the potato at the maximum point of its trajectory. Tangent theta is equal to the vertical displacement divided by the horizontal displacement. Given that we know the angle and we know the horizontal displacement, we can figure out what the maximum vertical displacement was, which was 87.8 meters. In our second calculation, we determine the time taken for the potato to reach the ground from the maximum vertical displacement in its trajectory. What we're referring to is the second half of the potato's trajectory, so from the point of its highest point in the sky to the point that it actually touches the ground. For this, we use kinematics. We use the simple displacement equation to solve. We got a value of time is equal to 4.23 seconds. In this next calculation, we determine the time taken for the potato to reach the maximum vertical displacement in its trajectory upon its departure from the barrel of the spud gun. The total time was subtracted from the previously determined value, and then subtracted from 0.23. 0.23 represents the delta t. After analyzing slow motion footage, 0.23 seconds was the time determined for the potato to leave the barrel of the spud gun from the initial combustion. Next, we determined the initial vertical velocity of the potato upon its exit from the barrel of the spud gun. For this, we also use kinematics, and we also use the displacement equation. With this, we found that the initial vertical displacement was 43.1 meters per second. In our next calculation, we determined the exit velocity of the potato from the barrel of the spud gun. To do this, we used some simple trigonometry. Since we know the angle of the spud gun with the Earth, we know that the vertical component of the exit velocity divided by the exit velocity is equal to the sine theta. We find that the exit velocity of the potato is 86.2 meters per second. In our final calculation, we determine the magnitude of the force exerted on the potato by the combustion of the hydrocarbon. Given the relationship m delta v is equal to f delta t, and plugging in those values, we find that the force applied to the potato over the course of 0.23 seconds is 58.8 newtons. What this implies is that the acceleration of the potato through the length of the barrel is roughly 374 meters per second squared. Its exit velocity, in more relative terms, is about 140 miles an hour. That's a pretty fast potato. Proper error analysis of the experiment is not possible, but it's safe to say that there's a significant degree of uncertainty when considering the measured values. Timing and horizontal displacement were particularly troublesome to determine, as it was often very difficult to start the timer right once I flicked the flint and steel, and it was often hard to determine exactly when to stop the timer once the potato landed. It was also hard to determine the horizontal displacement because oftentimes the potato would land and fracture into pieces, or it would land and bounce. I tried to fix these issues by wrapping the potato in certain materials, but that didn't seem to help very much. Temperature and chemistry also play an important role in variance in this lab. At lower temperatures, it's likely that the combustion reaction will be less successful, and the average kinetic energy of the gas particles produced will be less. This will cause a lower temperature magnitude for the total temperature difference on each side of the potato, causing the potato to maybe not go as far. The chemistry also plays an important role, as if not the same amount of moles of propellant are being used up every single trial, then it's safe to assume that the distance traveled of the potato will vary from trial to trial. Overall, I think this lab was a success. I was able to get very respectable numbers relative to the tools that I had for measurement. I could have taken several different approaches to this. I chose to use kinematics to solve for the force applied to the spud, but I could have easily attached the spud cannon to a pendulum and solved for impulse that way. In retrospect, that probably would have been better because I probably would have gotten more accurate data. There probably would have been less uncertainty in the data collection process. This concludes the presentation. I hope you enjoyed.